Hi everyone, this is video 1 for day 3 in week 4. So, recapping what we have so far, we are very good with solving right triangles now. We can pretty much figure out a bunch of stuff by constructing our own right triangles. We also know how to make sense of trig functions for any angle. Now, the obvious next question to ask is, well, what if I don't have a right triangle, right? So, those kind of triangles are called oblique triangles. That means there is no right angle. Now what we're going to do is we're going to use a classic method in mathematics, which is when you encounter something complicated, well, you break it down into something that you already know. So that's what we're going to do. Let's say triangle ABC is an oblique triangle. Now we are trying to find any information we can gain for this triangle using what we already know. What we know are right triangles. So I go ahead and I break this triangle into two right triangles. Now this is a process you can do with any triangle, right? You can break it down into two smaller right triangles. Now I'm going to do some labeling here, which is sort of like a rule or a method to keep things consistent. The method or the rule says this: if this point is capital A, then the side opposite to it, which is all of this, is labeled small case a. So B would mean this is labeled small case b, and if this vertex is C, then this is labeled small case c. And for convenience, I'm going to call this h, which is just the height. Now let's look at this triangle. Triangle ACD, sine of the angle C is opposite over hypotenuse, so it's h over b, which means cross multiplying h is b sine c. But if I take the triangle ADB and I look at sine of b, that is opposite over hypotenuse is h over c. Cross multiplying, I get h is c times sine b. But these are the same. That's the height which is shared by these triangles. So it has to have the same value, which means b times sine c should equal c times sine b. Now the nice thing here is there is no mention of h. Yeah, this relation is just between the sides and the angles of the triangle. Now I can make this look a little nicer by sort of reverse engineering it by saying that, well, this must have been the product of a cross multiplication. Right, so if I rearrange this, I can write this as sine c over small c is sine b over small b. You can verify. If you cross multiply, you end up here. This is a nice looking relation, right? It's very symmetric. You have a sine of an angle divided by the same side. Sine of another angle divided by the same side. And if you actually construct another, a different kind of right triangle from going from B, you'll end up with a very nice relationship which has a name, which is called the sine law, which says for any triangle, if you take the side divided by the sine of that angle, it equals the other side divided by the sine of that angle, which equals the third side divided by the sine. So I just flip these ratios, right? If two ratios are same, then their reciprocals are also the same. This is very neat because this does not require a right triangle. We used a right triangle to get to this relation, but the final relation has nothing to do with a right triangle. A, B, C are sides of any triangle. Capital A, capital B, capital C are angles of any triangle. Very useful relationship. Let's look at examples. Find x. So first of all, I identify. It has to be, remember, so by the naming convention, side A and angle A are opposite to each other. So they are facing. So to set this up, I identify x is opposite 39 and the 5.7 is opposite 62. So x over sine of 39 is going to equal 5.700 over sine of 62. Now instead of cross multiplying, what I'm going to do here is I'm trying to solve for x, right? So I'm going to keep the x and I'm going to multiply both sides by sine 39. So these cancel out. So what I get for x is 5.700 times sine 39 divided by sine 62. And this you can plug into the calculator directly. 5.700 times sine of 39 divided by sine of 62, which comes out to 4.627 if I round it inches. Okay, so not a right triangle, but we are still able to find the sides. Another example. Now here you have some labelings given. You're given angle 1 and angle 2, and you're trying to find small f and small g. Okay, so first of all, I have this side, so I need to find this angle E. Angle E is 180 minus angle 1 minus angle 2. We need to do some additional calculation here because these are not in decimal. This is 80 degrees plus 20 minutes over 60, so that's 80.33 degrees. And angle 2 equals angle 1, so it's also 80.33 degrees. So angle E is, let's plug that in, 180 minus 80.33 minus 80.33. It's 19.34 degrees. Alright, now I can, it's too dark, set this up. So 27.00 over sine of 19.34 equals, f corresponds to angle 2. So f over sine of 80.33. Now in this case I'm solving for f, so I'm going to multiply both sides by sine of 80.33, sine of 80.33, boom, plug that into the calculator. 27.00 times sine of 80.33 divided by 27.00 times sine of 80.33 divided by sine of 19.34 is 80.37 feet. 27.00 over sine of E, which is 19.34, equals G over sine of 80.33. Or you can skip this part because isosceles triangle, right? Angle 1 equals angle 2. So angle 1 equals angle 2 means isosceles triangle. So G equals F equals 80.37 feet. And you can also see it by this ratio. This is the exact same equation I had here. So obviously G is going to come out to be the exact same value. Okay, in the next video I'm going to cover situations like when is sine law, well, it can be applied in any triangle, but when does it give you meaningful results and when it fails to give you meaningful result. That's going to be in the second